go. We're going to restart it. All right. Okay, at the temperature 34.4 grams of ethanol. So I have a mass, 34.4 grams. From 25 to 78.8. So 78.8 minus 25 equals my delta T, which is 53.8 degrees change. Notice I haven't even looked what they're looking for yet. I'm just adding numbers to this. Oh, and I've been given the specific heat. Oh, they've made it very easy for me. They're just looking for Q. So that looks like 2.44 times 34.4 times 53.8 equals 4,515. Let's do it over here. 4,515 joules. Did I get it right? Did I get it right? Did I get it right? 4,515 joules. Yes, I did get it right. Good for me. It's almost like I'm good at chemistry. Sometimes. Okay. Next, 63, 155 gram sample. Again, I'm not even looking at what they're asking yet. Blah, 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 25 to 40, so that's 15 degrees delta T. Absorb 5,696 joules. Oh, it looks like I've got a Q. 5,696 joules equals. So I'm solving for C. Okay. So 155 times 15, enter. 155 times 15, enter. 56.96 divided by second answer, enter. Looks like 2.44. 2.44 joules per gram per degree centigrade. That is my answer for number 63. Let's see if I got that one right. 2.45 joules. Okay, I like it. I'm not rounding anything. Yeah, 2.449. Yes, that rounds up, doesn't it? Okay. Heating curve diagram. Okay. See, I don't know why they ask you this. 64 and 65, I'm really not interested in you knowing all that. I am interested in you knowing number 66 because, and let me, oh, someone's bugging me yet again. Okay. Let's see. Sorry about that, people. We got to answer some questions. Okay. Okay, we might as well answer. We might as well. God damn it. I hear you, people. I hear you. Okay, we might as well answer why. Potential energy changes here. Kinetic energy changes on the slopes. Potential energy changes here because you're breaking bonds, and the potential energy is in the bonds, so it's changing as you go, as you break bonds. I don't remember any of that on the final, but still, I mean, I guess it'd be good to know. Potential energy on the flats. How could you remember that? IP on the flats. Yeah, maybe you could do that. I don't know. Which letter represents a solid? Well, on your little chart, it's down here. It's the first slope, so that would be E. A liquid, that would be C, and that would be A. The little one at the end is the gas. A temperature change occurs during a phase change. True or false? Well, it's flat. We know that phase changes, all the action happens on the flats. No temperature change here, right? This is temp. So there's no temperature change. So that is false. Which letter represents vaporization? So vaporization is going to be right here. This is going to be B. What is condensation? Well, that's also going to be B, going the other way. And melting, that's going to be whatever letter they put here, D. Is a solid changing to a liquid endothermic or exothermic? Okay, well, if it's going from a solid to a liquid, I have to add heat in, don't I? I take ice cubes, I have to add heat into them to get them to turn into water. So that's going to be endothermic, right? It's exothermic when I turn water into ice cubes. And I know it doesn't seem that way, but I have to take heat out of the system. Okay, the unstable arrangement, where are we at? 70. The unstable arrangement of atoms. Well, first of all, let's put a reaction diagram on here. And then let's start defining things. The unstable arrangement of colliding particles that rearrange to form products is called the activated complex. And those chemicals that are not quite reactants and not quite products, they exist right at this hump, right? Energy needed to start a chemical reaction. Well, that looks like this. I got to get over this hill here. That is called the E sub A, or activation energy. Okay, this is a reaction diagram. This is a diagram of a reaction. This is a point on the diagram where the activated complex exists. It's not any part of this diagram. It is the actual chemicals in the beaker. The activation energy is on the diagram. It's this hill that I have to get over, right? By the way, is this endo or exo? It's endo. Of course it is. The products have a higher energy than the reactants. That energy had to come from somewhere. Okay. Energy stored in bonds is, what is it? Potential energy. Remember, we pee on the flats? Potential energy is stored in bonds. Hopefully they won't ask that question. That's number 72. All right, now we get a chart. And I drew the chart, and let's draw some letters, and let's figure out where it is. Okay, so we have this, and they call this B, and they call this A, and they call this C, and they call this D. Okay, activation energy. Well, it's B. It's the hill I have to get over, right? Reactants, that's A. Products, that's D. The activated complex exists at C. It's not a point on here. There's C, it's not C. It's not where this point is. It's the actual chemicals in the beaker form the activated complex, and this is when they form, is C. Does this energy diagram represent an endo or exo? Well, I just answered that a minute ago. It's endo. Okay, so we're through 77. And then we've got this weird chart. Factors affecting reaction rate. Well, the factors that are affecting reaction rate are, depending on their position in the periodic table, so that's reactivity. And then concentration. As concentration increases, reaction, and I'm going to start using the shorthand, reaction rate increases. Surface area. As surface, y'all are going to make fun of that. Surface area increases, reaction rate increases. Temperature, temp. As temp increases, reaction rate increases. Now we know that's not all the time, but whatever. Substance that changes the reaction without being consumed is a catalyst. Remember, it is not consumed. It It is not consumed. All it's doing is guiding the particles together so that they have more effective collisions. Okay. Okay. Now then. They have given us a reaction rate we have to calculate. And reaction rate is change in molarity over change in time. So it is final minus initial molarity. Okay, you observe a reaction pink to blue at room temperature. The time it took for the reaction rate if you heated the reaction to 80 degrees, what would happen to this reaction rate? Well, it would go down. The reaction rate, the time would go down. Okay. So 79, determine the reaction rate of 1.8 molar concentration H2S when it decreases. Okay, so it's final minus initial over final 14 seconds minus initial 0 seconds. So I get 14 seconds and I get a change in molarity of 1.3, and you can make it negative. That's perfectly okay to do. So I get 1.3 divided by 14 equals 0.092 molarity per second change. And it was a negative number, which just means it was going down, right? That my molarity was high and it went to something that was lower. That means it was disappearing. Negative numbers are okay for that, but if you don't see an answer that's negative, then by all means, just make it positive. Okay, determine the reaction rate, 3.2. The initial concentration is 0 molar since none remained yet. Okay, so we have final minus initial molarity. And we have final time minus initial time. So it looks like 3.2 over 18 seconds. 3.2 divided by 18 equals 0.177 molarity per second change. Easy enough. 81. Let's keep charging forward. 81 states that a system at equilibrium will shift back to equilibrium if when disturbed in order to reduce the stress. That is Le Chatelier. Le Chatelier, right? Is he Le or Le? Well, it's just Chatelier, so on the key it just says Chatelier, so we'll just go with that. Forward and reverse reactions occur at the same rate. When they are equal, when the forward and reverse actions are equal, we are at equilibrium. That's number 82. Oh, last page, folks. Let's see. We're at 13 minutes. We're going to keep going. We're going to keep going. All right, so they've given me a reaction. They've said 2N2H4, and it's a gas, plus 2NO2, which is a gas, goes to 3N2s, which is a gas, plus 4H2Os, which they're saying is a gas, plus 32 kilojoules. All right, so the energy is a product. All right, A, they're saying I add heat. If I add anything, it goes to the other side. So I've added heat, so it goes left. And then I'm adding water. All right, where's water at? Oh, water's here. If I add anything, it goes to the other side. That's left. And then we're increasing volume. Now the problem here is that you probably don't know that increasing volume decreases pressure, but you just got through gas law, so hopefully you do know that. If I decrease pressure, it runs to the side with the most moles. If I increase pressure, it runs to the side with the least moles. This side has 2 plus 2 is 4. This side has 3 plus 4 is 7. So if I increase the volume, then I'm decreasing the pressure and it's running to the right. Don't feel too bad if you didn't catch all that. Removing into H4. If I remove something, it runs to that side. So I'm removing this, so it runs to the left. If I remove nitrogen, okay, that's nitrogen, moves to the right. By adding NO2, it's going to run away from that. NO2 is on the reactant side. It's going to run that way. Removing H2O. Again, if I remove something, it's going to run to that side. That side, adding helium. Well, I don't see helium. Do you see helium? I do not. So if I add helium in, it just becomes another product, right? Equilibrium's not really going to be affected because it's a spectator, because it's not involved in any of this. So, okay. All right. My little lunatics. Let's see, what time is it? 4 o'clock. Oh my goodness, I've been here forever. Okay. Where are we at? Where are we at here? What's going on? Hess's law. Hess's law, all you got to know is that you add those two numbers, the kilojoules. 185 plus 73. Okay, so let's do this. 73 plus a negative 185 equals 112 kilojoules. Negative 112 kilojoules. That's it. That's all Hess's law. You'll see the evils of Hess's law later. Okay. Okay, we've got our gas laws. Okay, so Boyle's law will increase if pressure decreases, assuming temperature is held. So Boyle's law. Volume will, wait a minute, where are we at? Oh my god, I gotta look stuff up. Jeez. Where are we at? Okay, volume will increase if pressure decreases, assuming temperature is held constant. Volume will increase. Okay, let's look at this. V1, P1 equals V2, P2. All right. Okay. If pressure decreases. So I'm going to say I have a pressure of 2, and it decreases to a pressure of 1 atmosphere. And then I'm going to say I have a volume of 1, and let's see what happens to that volume. 2 times 1 is 2, divided by 1 is 2. My volume increased. No problem there. But you can test all of these. All you have to do is throw in numbers and you can know exactly. So Charles' law, temperature will increase if volume increases, assuming pressure is held at a constant. According to Gay-Lussac, or Gay-Lussac, whatever you want to call him, pressures will decrease if temperature decreases, assuming volume is held constant. If you buy a helium balloon at the grocery store and then take the balloon outside to your car on a hot summer day, what will happen to the volume of the balloon, assuming the pressure is constant? Volume will increase. It's just the opposite. If I take a balloon and I take it and put it in the freezer and it will shrink down. Okay, use the appropriate equation to solve the problems below. Well, I'll tell you what, I can solve all of them using ideal or combined gas law. So in number 1, it looks like I have 900 milliliters at a temp of 57 degrees. 900 milliliters at a temp of 57 degrees. Oh, can I use 57 degrees? No, I cannot. I have to use Kelvin for all these. 57 plus 273 equals 330. and equals, and then what is the volume? X volume at 100, and what does this say? 132. 132 plus 273 equals 405. All right, let's do some calculating. 900 divided by 230 equals times 405 equals, I believe I have 1104.5 milliliters. This is just a game called Solve for X. And if you know P1 V1 over T1, P2 V2 over T2, then all of these get really easy. Okay, 2.7 liters at 1.998 atmospheres and 36 degrees. If it is released and rises to an elevation at which the pressure is 0.9 atms and 28 degrees, what is the new volume of the balloon? Okay, so I have 2.7 liters and 1.998 atmospheres, and I'm going to put T1 over here because it makes me happy. 273 times 273 plus 36 equals 309. Put temp 1 over here, 309 Kelvin times. Okay, so I have, what am I at? 2.7 liters, 1.998 times 36 degrees. 28 degrees is my T2, so 28 plus 273 equals 301 degrees, and released to an elevated 0.9 atmospheres. Looks like a combined gas law problem. So I'm solving for, what am I solving for? Oh, volume. So let's do this. Let's do 2.7 times 1.99 times 301, enter, divided by 0.9 times 309, 5.81 liters. Am I right? Is he right? 5.85 liters. Okay, well, within the margin. I'll allow that. Okay, 92. Closed gas container. So my volume is fixed. So it looks like I have two pressures and a temperature. So 12 atms and 16 atms. And I'm going to go back and forth between these. And the original temperature was 25, which is 298. Then I need X temperature. Okay. So, divided by 98. There. 16 divided by second answer, enter. Looks like I have 397 degrees Kelvin. Am I correct? Yes, I am. 93. A sample of oxygen gas occupies 6.0. Well, I guess I should get this out of the way. A sample of oxygen gas occupies 6.2 liters at STP. Well, I know that STP is 273 degrees. How many grams does that represent? Oh, that's too easy. 6.2 liters of gas. And how many liters of gas are in 22.4 liters of gas per mole? So this will tell me how many moles. 6.2 divided by 22.4 equals 0.276. This is liters per mole. These cancel this, so what I get is, what, 0.276 moles. By now, you better be able to convert moles to grams. If you don't know, 1 mole, 16 grams of, what are we looking at here? Oxygen gas. Ooh, no, 32 grams of oxygen gas. So, what is 32 times 0.276, Alex? It is 8.832 grams. 8.832 grams. I think I agree with, yeah. What volume will 4 moles of gas occupy? Wow, that's too easy. 4 moles. We know that each mole is 22.4. 4 times 22.4 liters, moles per mole. That gets rid of moles. 4 is, what is that? That is 89.6 liters. Yes. 89.6 liters of gas is what that'll take up. How many moles are in 45 liters? Too easy. Hopefully these are really easy for you too. 45 liters. Well, how many moles are in it? Divided by 22.4 liters per mole. That gets rid of liters. And I'm telling you right now that it's going to be 2 point something. Yeah, 2.0. 2 moles. Guys, that concludes all of the teaching of chemistry that you're going to get from me this year. I hope that you do really well in the final. I hope that this helped out. It really has been a pleasure teaching all of you. I'm going to miss all of you terribly, and hopefully you'll come by my room and see me. All right, guys. See ya.